In this lecture, we're gonna do a review of the memory hierarchy concepts that we have been studying since we started studying the memory hierarchy and we started studying caches. So the idea of this lecture is to put everything together and to enable us to understand the parallels and the similarities between the different levels of the hierarchy. So there are common principles that will apply to all the levels of the memory hierarchy, and of course the principle of locality, both spatial and temporal locality, are very important throughout the hierarchy for all the different aspects. And all these principles are based on the notion of caching. And the notion of caching is something that we use in our everyday life all the time. We store things near to us that we're going to need to use again in the future. And that is a human nature to do this kind of caching. And many animals do caching as well. But in computer systems, at each level in the hierarchy, we have the issues to solve, that is the block placement. So giving a block that comes from the lower level, where can I place that block? And that is an issue that has to be solved both for the caches and for the memory system. The other issue is, how do I find a block? For example, if I have a full associative memory, then to find a block, I have to search through all the blocks to see if I can match the tag. If I have a directly mapped cache, I can just decode the index and find one location that's the only location that entry could be. If I have a set associative cache, I'm going to do a combination of those. I'm going to use an index to find the set, and then I'm going to have to iterate through the set, or I can do that in parallel as well, but I'm going to have to compare my tag with all the tags that are in the set. The other issue is what I do if I have to do a replacement when I have a miss, because I need to make room for another block into the upper level of the hierarchy, and what's the policy that I use to do that. Another aspect of the definition of each level of the memory hierarchy, what is my write policy? And as we've seen, that I have a write policy for writes that miss the cache and for writes that hit the cache, and what I do in that case. So looking at block placement, the block placement is determined by the associativity. So if I have a direct mapped cache, there's a one-way set associative cache. In that case, there is a direct placement, and all I need to do is to decode the index. So there is only one choice for placement in a direct mapped cache. If I have an any-way set associative cache, then there will be n choices inside the set of where I can place this block. And if I have a full associative layer in my hierarchy, then I can put this new block in any location in that layer. The higher associativity will reduce the miss rate because I have fewer conflicts. I have fewer instances where a block needs to come in and it has to evict another block, even though there are other places in the cache that are not being utilized. It does increases the complexity, increases the cost, and increases the access time, because the higher the associativity, the more blocks I need to search. In hardware, I can do that search in parallel. I still have to have more entries in the muxes, which can make them slightly slower, and I will be consuming more energy. So to find a block, depending on the associativity, so if I have a direct mapped layer, the location method will be the index. There will be only one tag comparison. With an any way set associative cache, I'm going to use an index to find the set, and then I'm going to search the entries in the set, and there will be n tag comparisons. If I have a full associative cache, then I search all the entries. I have to compare the number of entries, or I could use a full lookup table, in which case the tag comparison could be 0, because in a full lookup table, I will take the full address and I will look it up. For hardware caches, they will reduce the comparison. I wanted to reduce the comparisons to reduce the cost, and this cost can be in terms of area in the chip, or could be in terms of the energy that I consume. For virtual memory, a full table lookup can make a full associative cache viable, And we saw some ways in which we can approximate the least recently used algorithm if we have a full table lookup. And the benefit is that I can reduce the miss rate in that case. For the replacement, I have the replacement is the choice that I make of the entry that I'm going to replace when I have a miss in a given layer of the hierarchy. The most efficient way to do that, or the highest efficacy, is if I use the least recently used method. It's complex, it's costly and harder if I have a higher associativity. It works very well for an associativity of 2, but it becomes more complex with higher associativity. A random selection method is close to the least recently used method, and it's much easier to implement. And we saw that one solution that we have is to do that solution where I never replace the most recently used entry. In virtual memory, I can do a least recently used approximation with hardware support. As you remember, I have that extra bit that I will turn on whenever I have an access. In the RISC-V status register, I have, or RISC-V page entry register, I have a bit that says whether that entry has been accessed. For my write policy, I can have a write through policy where whenever I write, I update in both the upper and the lower level of the hierarchy. It will simplify replacement, but it probably going to require a write buffer because I'm doing constant writes. I can have a write back policy that will update the upper level only of the hierarchy, and the updated lower level will be done when I replace a block. I need a dirt bit, so I need to keep more state. I need a dirt bit to mark the page that are the entries that have been changed, or the blocks that have been changed. In virtual memory, only the write back policy is feasible because of the latency. The latency is the amount of time that it takes to write to the disk. It's too large, it's too high, so the only policy that makes sense is the write back policy. What are the sources of misses in my cache? I have compulsory misses, that is cold start misses. So this is the first access to a block. A block has never been accessed, it cannot be in the cache. I have capacity misses, that is because the cache size is finite. So, and capacity misses occurs where I will replace a block because I don't have more space in the cache, and later I access that block again and I get a miss. And I have conflict misses that also call collision misses. That is, if I have a cache that's not full associative, I will have these misses because of competitions of multiple entries that are trying to go into the same set, and the set doesn't have space for all the entries. Conflict miss cannot occur in a full associative cache because in a full associative cache, any block can go anywhere, and the only case where I then would have a miss is a capacity miss because I have filled the entire cache and now I have to throw away something. And there is another type of miss that's not listed here, that is the coherence miss. We're going to talk in a little bit about cache coherence, and that occurs when you have multiple processors in a system, each one with their own cache, and the caches needs to be made coherent, and what we're going to happen is that I'm going to have to invalidate an entry in the cache because another processor has written to it. There are several trade-offs in the design of a cache. One change that I could do to a cache, I could increase the cache size. If I increase the cache size, I'm going to decrease the capacity misses because I have many more entries in the cache. The negative effect is that I may increase the access time because now I have many more bits in the decoded of the index, for example, or many more sets to access. I can increase the associativity. If I increase the associativity, I decrease the conflict misses because there will be more entries per set, so there will be less competition for those entries, or I can have more blocks that can be in those sets. And the problem with that, or the negative effect, that I may increase the access time because now I have to search for I need to do more comparisons. And depending on how the comparisons are done, I may either increase the access time or I may increase the consumption of energy in the cache because I'm going to be duplicating the hardware. I can increase the block size. Increasing the block size will decrease the compulsory misses because when I miss on one address, I'll bring in many more words from the memory because of that miss. So one way that we can think about a larger block size is that I have this free prefetching. Because more words that are likely to be used in the future are used. So one of the problems is that I may increase the miss penalty because now I have to spend more time bringing this larger block from the lower level of memory to the higher level of memory. If I have very large block sizes, then I may increase the miss rate actually because of pollution. Pollution happens when I bring data from the lower level to the upper level, but I never use the data. That's called cache pollution. And you can do a quick thinking exercise. In the extreme, I could make a block the size of the cache, so the entire cache has a single block. So anytime that I have a miss, I replace the entire cache. That's actually a pretty bad idea, right? But this thinking exercise leads you to believe that there is a trade-off. Perhaps a block of size 1 word is not good, but a block that is the size of the entire cache is not good either. So I need to find a sweet spot in between that will be, I'm gonna get enough free prefetching, decreasing the compulsory misses, but I'm not gonna be increasing the misses because of the cache pollution, and my miss penalty will also be manageable. Another topic that I want to talk about in this lecture is the idea of virtual machines. Most of you would be familiar with virtual machines. Some of you probably use virtual machines in your computers. So a virtual machine is a system where you have a host computer that's emulating a guest operating system and the machine resources for the guest operating systems. So the idea is to improve the isolation between multiple guests in a machine. So virtual machines are very popular with cloud computing actually because the provider of a cloud computing system can have a single hardware and provides many virtual machines to either the same client or multiple clients. The main idea of the virtual machine is that you're going to avoid some of the security and reliability problems that you have if you don't use the virtual machine, if you have just processes sharing access. And it's very helpful to share resources, and that's why it's very popular in cloud computing. But virtualization has performance impact. It's very feasible for modern high-performance computers, and that's why it's very popular these days because it allows me to provide these services. Examples of virtual machine would be a virtual machine for the IBM 370. This is 1970s technology, so there is nothing new with virtual machines. It's just that what happens today is that there is enough processing and memory capacity in the machines that we can use virtual machines for many more applications than we could use in the past. Other ideas of virtual machines is VMware and the Microsoft Virtual PC. A virtual machine monitor will be mapping the virtual resources to physical resources. So your virtual machine must have access to memory, to I/O devices, to CPUs, etc. And this monitor will provide this access. So the guest code will run on native machine in user mode. And then I will trap to the virtual machine monitor whenever any privilege instruction is executed, and it will access access to protected resources. So the idea here is that I actually running the user code on the native machine for performance and efficiency, but anything that is not user level will be handled by the virtual machine monitor. The guest operating system can be different from the host operating system, and in many cases it is. And a virtual machine monitor can handle real input-output devices by providing these generic interfaces to input-output devices for the guests in the machine. An example, for example, is a timer visualization. So in the native machine, when there is a timer interrupt, the operating system will suspend the current process, handle the interrupt, select and resume the next process. With a virtual machine monitor, the virtual machine monitor will suspend the current virtual machine, will handle the interrupt, and will select and resume the next virtual machine. So instead of you can see the description is pretty much the same. The only thing that changes is that we are not handling processes in a machine, but we are handling virtual machines. If a virtual machine requires timer interrupts, the virtual machine monitor can emulate a virtual timer. So it will emulate the interrupt for the virtual machine when the physical timer interrupt occurs. So basically you program the timer in your real machine. When your real machine does a timer interrupt, the virtual machine monitor will understand that this is not an interruption that was being expected by the virtual machine, and will pass on that interruption to the virtual machine to be handled according to the operating system of the virtual machine. Another topic that we want to talk about in this lecture, so this lecture is a collection of different topics and a bit of a review, is the problem of cache coherence. So the problem of cache coherence is the problem that I have multiple processors, and you're going to see in a minute a picture that we have multiple cores inside a single chip even. So we have multiple processors, each one with their caches, and if they are accessing the same memory space, so the same address space, so they are sharing pages in their access to memories, they will be caching values in their cache that can be the value that can be the same address. In that case, what can happen, and here is a sequence of things that could happen. Let's say that I have a memory location that at time 0 has the value 0. At time 1, there is a CPU-A that reads the value of X. So the CPU-A copies the value 0 from the memory into its cache. Then at time 2, step 2, CPU-B also reads the value of X. So the CPU-B also makes a copy of the value of X in its cache. And then at time 3, the CPU-A writes the number 1 to that memory location, to the variable X. And now we have the situation at the bottom of this table here, where the CPU-A has the value 1, and the CPU-A may have even written it back to memory, so memory has the value 1. But if I don't do anything, CPU-B will have the value 0, which is the old value. And if CPU-B reads again that location, so let's say that that location was read in a loop and now I go back to the loop, it will not gonna get the most recent value. It will gonna get the value that it had loaded when it first accessed the value. So this is what we call a stale value in the cache. And if we want the caches to be coherent, we cannot have stale values. So we need to first define what coherence means. Informally, we wanted to say that the reads will return the most recent written value to a variable. Formally, we can say that if a program P writes the value of, or processor P writes the value of X, and P reads the value of X with no intervening writes, then the read must return the value that was written. So for the same processor, if I write and sometime later I read the value, I want to read the value that I wrote, as long as there are no intervening writes between those two operations. In a multiprocessing system, I can have that P1 writes the value of X and P2 reads the value of X. And let's say that this P2 read is sufficiently later. In that case, the read must return the written value. And now we have a very tricky thing here that we have to define what sufficiently later is. And that is where the solutions for coherence come in. So one example would be the CPU-B is reading the value of X after the step 3 in the example where we had, where CPU-B has the stale value. So the idea of coherence is that CPU-B cannot read the stale value. It has to read the new value. The other situation is that P1 writes the value of X and P2 writes the value of X. So those are two writes by two different processors. So the idea of coherence here is that all processors in the system should see those two writes in the same order. So it cannot be that P1 propagates its write to another processor P3, and then P2 propagates its write to processor P3, but there's a processor P4 that sees the write of P2 before the write of P1. So all processors in the systems should see all the writes in the same order. So in this case, if we have this guarantee, we will end up with the same final value for the variable x. So what we need in order to enforce coherence is something called cache coherence protocols. So cache coherence protocols are operations that are performed by the caches in multiple processors to ensure that we have coherence in a machine that has multiple processors. And the idea is that we can have migration of data to the local caches, or the data can migrate between caches. The idea is to reduce the bandwidth to access the shared main memory. So the idea is if a processor writes a new value, that new value can be propagated to the cache of another processor without having to write it back to the main memory. We do study in great detail the cache coherence protocols in 429. This is just a very high overview to give you an idea of how coherence is done. So I can have replication of read shared data, for example. So if I have multiple processors reading the same data, but nobody is writing, I can simply make a copy of that data in the cache of each one of the processors, and each processor is going to have hits into their caches when they read the value. I can have something that's called a snooping protocol. A snooping protocol consists in each cache being monitoring all the reads and writes that happen in the system. So they are snooping and they are seeing everything that's going in the bus, and then they are taking action with their own values that they have saved from previous operations to make sure that they are consistent. So in the snooping protocol, the idea is that, for example, if I have a local copy of a value and I snoop the bus and I see that another processor has written to that value, I can simply invalidate my copy. In this way, this is called an invalidation protocol, and in this way, if my processor asks for that value sometime later, I'm not going to have the copy that would have been stale by this time, and I'm going to go out and find the fresh copy. And in the snooping protocol, then what's going to happen is that when I need a value, instead of saying I got a miss, I need to go to the memory, I say I got a miss, I'm going to send a request to all the caches of all the other processors to see if they may have the most recent value. If one of the caches has the most recent value, that cache will answer me and say, here is the most recent value, and I don't need to go to the memory. There are directory-based protocols. The idea of the directory-based protocol is that the caches and the memory have a record of who has a copy of each one of the locations in memory. So that, for example, if I need to invalidate giving address because I'm doing a write right now, I can simply send a message to the processors that are the caches that have a copy of this value, and I do not need to send a message to everybody, which could be expensive. So here is an example with an invalidating snooping protocol. So we have a sequence of operations like before. What we had before is that the two CPUs both read the value, and then the CPU A writes the value, and we had stopped at this line here where CPU A writes the value before, and we had this stale value for the CPU B cache. What we are doing now with the invalidate protocol is that when the CPU A writes this new value in its cache, it sends a message invalidating that address in all the caches of all the other processors. So CPU B now, after this operation, does not have a copy, does not have a stale copy, doesn't have the value at all. Then when CPU B reads that value, that will be a miss. And usually we have learned that a miss goes to the memory and can take a long time. What we have now is that these caches are connected by a bus, and the CPU B can send a request, and the CPU A cache can detect that someone wants that value and can send the new value without we needing to go to the memory. So the cache gets exclusive access to a block when it is to be written. It will broadcast an invalidate message to the bus to say, I'm going to write this. If anybody has a copy of it, you need to get rid of your copy because your copy will be stale after my write. And then, so any subsequent read by any other cache after I have done my write to the invalidation will be a miss, and the message will be sent to everybody when that miss happened. And then I now am the owner of that value because I was the last one to write it. So I'm going to supply the value when that request comes into the bus. We have the idea also of memory consistency. The memory consistency is addressing the question of when should writes be seen by other processors. So seeing means that a read returns the written value. This cannot happen instantaneously because there are delays in the system for propagation. So the assumptions for memory coherence is that a write completes only when all the processors have seen it. So just writing to my own cache is not enough. All other processors have to have seen it, only then the write is completed. But note that in the case of invalidation, just the fact that I invalidated every else's value is the equivalent of it's being seen. So a processor cannot reorder the writes with other accesses for this type of consistency. The consequence is that if a processor P writes a value X and then writes a value Y, all processors must see the new Y. That all processors that see the new Y also must see the new X. You cannot just see the new Y and not see the new X. So the processors can reorder the reads, but they cannot reorder the writes. So I'm going to stop this part of the lecture here. We have been going on for quite a while already. Let me just find the stopping button here.